It's crazy. And yeah, so in this spirit, it's my pleasure to also announce the last speaker of this conference, Akhil Mathew. And he will talk about p-adic etale tate twists and syntomic cohomology, I believe.
Okay, yeah. Thank you very much for the invitation. And also, since I'm the last speaker, I want to take the opportunity to thank all of the organizers and the Fields Institute for arranging such a wonderful event. Yeah, so it's really a great honor for me to speak here. I first had the opportunity to meet Peter 7 years ago in Berkeley. I was a beginning graduate student at the time. Peter is incredibly encouraging and incredibly generous with sharing his ideas. And yeah, I mean, really everything I've worked on since then has been very strongly influenced both by Peter and his mathematics. So thanks. Okay, so let me start the broadcast. Screen share. Sorry. Yeah, so sorry. So I changed my title very slightly. So so this is going to be based on some joint work with Bhargav Bhatt, and it's, I guess, about sort of the interaction of some of the ideas that have been developed by Peter and his collaborators with K-theory. So this is basically the setup. So let X be a quasi-compact and quasi-separated scheme. So then we can associate to X the K-theory spectrum, the algebraic K-theory spectrum K of X. So this is some spectrum. And well, let me just say, I won't try to define, but let me just say that it's extracted from the stable infinity category of perfect complexes on X. And well, it's extracted in some sort of homotopical manner from this. And so we can assign some groups Ki of X. So for I an integer, and these are the homotopy groups. So these are given by the homotopy groups of this K-theory spectrum, K of X. And also, I want to consider the K groups with mod M coefficients. So Ki of X with Z mod M coefficients. This is pi I of the spectrum K of X mod M. Right, so I guess, right, so these K groups are typically, so I guess what I should say is that K0 is related, or it's essentially, it's a Grothendieck group, it's a usual Grothendieck group. And K1 has something to do with invertible functions. It's basically in terms of invertible functions on X, at least locally. But in general, the higher K groups are somehow very, very difficult to calculate explicitly. But there's a theorem of Gabor and Suslin that states that if you work with schemes on which M is invertible, then you can calculate these mod M K groups etale locally in a very sort of simple fashion. So let me write Ki etale with Z mod M coefficients to mean the etale sheafification of Ki with Z mod M coefficients. So there's the following theorem. So this is again due to Gabor and Suslin. Well, it's really sort of the combination. It's a combination of two results, and it states the following. So for any I greater than or equal to 0, and on the category of Z adjoin 1 over M schemes, I guess I'm always going to be assuming schemes are QCQS. Then one can give the following sort of complete description of the etale sheafified K groups with mod M coefficients. So K2I etale with Z mod M coefficients is given by mu M tensor I, and K2I plus 1 etale with mod M coefficients is just 0. Right, so it's saying that although, so in general, the K groups with mod M coefficients can be complicated. For example, they're like related to Chow groups or something. when you work etale locally on Z adjoin 1/m schemes, well, first of all, you can always annihilate odd degree classes. So if you have an odd degree class, you can always sort of annihilate it after passage through an etale covering. And in the even degrees, the classes are I mean, they just come from the usual sort of tate twists, um, tensor I. And I think this is kind of a remarkable theorem because also you're getting the same answer independently of the scheme, even though the K-theory can sort of look wildly different. Okay. So yeah, so essentially what I wanted to talk about today is to try to sort of explore analogs when M is not invertible. So what happens if M is not invertible? So yeah, so already this fails for sorry. So if M is not invertible, already the second part fails for K1. So already the second part fails for K1, and that's because, well, I mean, you want to take mth roots of units. So I mean, K1 is related to units, and you want to be able to take mth roots, and that's no longer sort of etale. So you need to work with sort of a finer topology. And there's an idea, and so this idea is due to Uziel, and it's also used by Batmaro-Schulze. Henceforth BMS2, which is that you should study these K groups not in the etale topology, but in the syntomic topology. So the idea is to study, so if you don't assume that M is invertible, what you should do is you should take the K groups again with mod M coefficients and study their sheafification in the syntomic topology. Syntomic right. Yeah, so I guess henceforth I'm going to take M to be some power of a prime number. M is given by p to the n. And so the idea is to study the sheafifications of the K groups mod M or mod p to the n in the syntomic topology. And so, right, so let me remind you, so the syntomic topology so it's a Grothendieck topology, which is generated by faithfully flat and LCI morphisms. So in particular, adding roots of elements, or really adding the solution of any monic polynomial equation is a syntomic cover. So locally in the syntomic topology, you can assume that every sort of monic polynomial has a root. And what I wanted to explain is that you can sort of do some of like this Gabor-Suslin is sort of an analog in the syntomic topology, at least in some cases. Okay. So right, so I should say that also this idea of sheafifying the syntomically sheafifying the K groups with mod p to the n coefficients is probably not a reasonable idea completely generally. One needs to assume that the schemes or the rings that you're working with have sort of mild singularities. And so let me make the following definition. So this is due to BMS2, or sort of slight variant of BMS2. So we're going to say that a ring R is p quasisyntomic if so first of all, we're going to assume that R has bounded p power torsion. And second, what I'm going to assume is that so I'm going to assume sort of a Tor amplitude condition on the cotension complex. So for all R mod p modules, M, when you form if you take the cotangent complex of R over Z and take the derived tensor product over R with M, this lives in the derived category of R, and I'm going to assume it lives in cohomological degrees greater than or equal to -1. So yeah, so this is some homological bound on the cotangent complex. And let me give the basic examples. So the basic example is that any LCI Noetherian ring is going to have this property. And another example is that if you have a perfectoid ring and take the quotient by a regular sequence, then it's going to have this property. So a perfectoid ring modulo a regular sequence is going to have this p quasisyntomic property. Okay, right. And so also this definition naturally globalizes for schemes, so it makes sense to say that a scheme is p quasisyntomic. Okay, so with this in mind, there's the following, I think, really beautiful theorem. So this is, I guess, called the odd vanishing theorem. And it's a recent theorem of Bott and Schulze. So it's proved in their prismatic cohomology paper. And it states the following. So on a p quasisyntomic scheme, right, so on p quasisyntomic schemes, for any I greater than or equal to 0, the syntomic sheafification of the odd degree k groups is 0. So k 2i plus 1 syntomically sheafified with z mod p to the n coefficients is 0. So as I mentioned, it's not true that right. So it's not true that if you have an odd degree K theory class with mod p to the n coefficients, you can annihilate it after passage to an etale cover anymore. But the statement is that if you're in the setting of the p quasisyntomic scheme, for example, an LCI Noetherian scheme, then you can annihilate these odd degree classes after passing to a syntomic cover. Yeah. So let me say just a little bit about the proof. So right. So this is so first of all, this is already a consequence of Gabbard-Suslin's theorem if you work with schemes when p is invertible. So really, sort of the action is the action is taking place for, say, p complete or p Kinselian rings R. Right. So also, because we're working in the syntomic topology, we're allowed to do things like take lots of p power roots of elements, and so we can more or less reduce to the case of the second example just by taking lots of p power roots. We can sort of assume that you have a perfectoid modulo a regular sequence. So can work with perfectoid with modulo a regular sequence. And if you're working, if now you're in mixed, right? So I should say that if you're in the setting of perfectoids mod regular sequences, then the p-adic K theory turns out to be closely related to the prismatic cohomology. And using this, for example, you can see that if you're an equal characteristic, then you're already done. So if you're an equal characteristic, if you have a perfect modular regular sequence, you sort of already have this odd vanishing. But it's actually quite a bit sort of more subtle and mixed characteristic. It's not quite enough to work with perfectoids mod regular sequences. You can still have some odd degree classes. But it turns out it's okay if the perfectoid ring has sort of sufficiently many p power roots. So if the perfectoid ring that you're working over has sufficiently many p power roots. So an essential ingredient is played by Andre's lemma. And actually in the form that is proved by Sesnovicius and Schulze. So essentially, you assume that your perfectoid has enough p power roots and even sort of absolutely integrally closed, and then you can sort of do a calculation, a sort of very clever calculation that Bott and Schulze do in prismatic cohomology to see this odd vanishing. Now, okay, so what I wanted to say something about in this talk is, well, what happens in even degrees. So this is some sheaf in the syntomic topology. And yeah, so just for convenience, it'll be nice not to work with syntomic sheaves, but sort of with etale sheaves. So we're going to sort of push this forward to the etale site. And then we make the following definition. So X is going to be a p quasisyntomic scheme sort of throughout. And I'm going to define an object z mod p to the n twisted by I sub x. So this is going to be some object in the derived category of etale sheaves on X. And this is going to be the derived push forward of the syntomic sheaf, K2I syntomic fully sheafified with z mod p to the n coefficients to the etale site of X. So you have this sheaf on the syntomic site that just comes from K theory with mod p to the n coefficients, and you push it forward in the derived sense to the etale site, and then you get this object, which I'll call z mod p to the n twisted by I sub X. And so I'll say more about this, but some of the notation should remind you of Tate twists. I'll also write z mod p to the n sub I of X to be R gamma of over X of z mod p to the n twisted by I sub X. Okay, and so the idea is that this is supposed to be some sort of general form of p-adic etale motivic cohomology in this context. Okay, so let me give some examples. So first of all, that these complexes, right? So they're supposed to remind you of Tate twists, and in fact, when you restrict the locus where p is invertible, they are exactly the Tate twists. So I guess I'm going to use this notation a lot in the future. So let J be the inclusion from X adjoin 1 over P to X. So then as a consequence of Gaber-Suslin, what you have is that J upper star of z mod P to the n twisted by I sub X is just the usual Tate twist, mu P to the n tensor prime. So in P is invertible, these are the usual Tate twists. Another example, so this so it follows from work of Geisser and Hesselholt. And it states that if X is a regular FP scheme, so then, well, I'll just say with mod P coefficient. So then this object FP of I sub X is an object that's sort of familiar in p-adic arithmetic geometry. Namely, it's this omega I log shifted by minus I. And this omega I log is this logarithmic differential form. So it's those I forms that you can build up from like wedge powers of dx over x, or wedge products of dx over x. Okay. So then there's some low degree examples. So right, so z mod p to the n twisted by 0 sub x is just a constant sheaf, z mod p to the n, and z mod p to the n twisted by 1 sub x. Well, it's generally not just in degree 0, but it's the mapping fiber of gm to gm given by multiplication by p to the n as a complex in the etale topology. Right, and so as a consequence is that you get a Kummer map, which goes from OX cross to the first cohomology of z mod p to the n twisted by 1 sub x. Right, and so this is surjection. Right, sorry. So there's also the following example, which is due to BMS2. So right, so as I mentioned, these z mod p to the n of I sub x, they're determined that their restriction under J upper star is just the usual Tate twists. But you can also describe the restriction to p equals 0. So let I from x mod p sitting inside x be the closed inclusion, and then you can describe I upper star of z mod p to the n twisted by I sub x. So this is now going to be a complex of sheaves on x mod p, or on the formal p-adic formal completion. And so namely, it's the following. So what you can do is you can consider the prismatic cohomology of, well, really the p-adic formal completion of x. Just write it as x. And you can consider, well, so this prismatic cohomology carries a Nygaard filtration. And I'm going to take the ith piece of the Nygaard filtration. And then, well, first of all, I can include the ith piece of the Nygaard filtration into x. Sorry, that was supposed to be a shorter arrow. Just sort of the inclusion. And then furthermore, well, prismatic cohomology carries a Frobenius. And if you, well, up to a twist, you can sort of make the Frobenius divisible on the ith Nygaard filtration. So I'm going to insert an ith Broykiss and twist. And there's an ith sort of ith divided Frobenius that comes from this. And And right, so then the formula that's given by Blattmore-Schulze is that it's the equalizer of these two maps, modulo, well, in this case, so modulo p to the n. So right, so when you consider this z mod p to the n twisted by I sub x, away from p, it's just the usual Tate twist, and somehow at p, it's the sort of filtered Frobenius fixed points of prismatic cohomology. So it's sort of some way of gluing the BMS2, these complexes introduced by BMS2, and the usual Tate twist on the generic fiber. I should also say that, yeah, so K-theory gives you sort of a convenient way of doing it, but you can also define these complexes z mod p to the n phi in other ways. So Mathew Morrow sort of sketch one in his talk earlier, and also Bad and Lurie have another construction, sort of purely algebraic. Okay. Right, and so today the goal is to describe z mod p to the n twisted by I sub x in a class of examples. Okay, so how might we try to understand these objects z mod p to the n twisted by I sub x? So as I said, if you restrict the locus where p is invertible, you're getting the usual Tate twists. So right, so by adjunction, you have a map from z mod p to the n twisted by I sub x, which goes to Rj lower star of mu p to the n tensor I, like this. So J, again, is the map from x adjoin 1 over p to x, just the inclusion. Okay, so you always have sort of a comparison map from these objects to the usual Tate twists. And basically what I want to do is sort of refine this map in various ways. And eventually we're going to get something that is often going to agree with z mod p to the n. Okay, so we're going to use the following fact. So the first sort of refinement is we use the following fact. So this was proved with Antio, Morrow, and Nicolaus. And it states that z mod p to the n twisted by I sub x always has this sort of cohomological bound. It always lives in degrees from 0 to I on x. So we can refine the above map just to the I truncation. So the above map refines to z mod p to the n to tau less than or equal to I of Rj lower star mu p to the n tensor I. So by connectivity. Okay, so that's the first refinement, and now we're going to do one more fact. We're going to need one more fact, which is that if you look at what happens, so I said that these z mod p to the n twisted by I, they live in degrees 0 to I, but you can also say something about the top. You can also say something about the top degree cohomology. So recall that so in weight 1, you have this Kummer map. So in weight 1 you have a surjective Kummer map from OX cross to H1, so to H1 and as a sheaf of z mod p to the n twisted by 1 of x. And in general, what happens is that these top degree cohomologies are always generated by H1. So in general, this direct sum over all I greater than or equal to 0 of the top degree cohomology of z mod p to the n twisted by I sub x is generated in degree 1. Right, and so in particular, that means that it's a quotient. So in degree 1, you have the Kummer map, which goes from units into H1, and this means that Hi of z mod p to the n twisted by I sub x is a quotient of OX cross tensor I. And so, yeah, so I guess these classes are called symbols. Yeah, and so in fact, you can say a little bit more about these top degree cohomologies. So I refer to work of Luders and Murrow for this. But I would just need this fact here. Okay, so right. So in particular, this is saying that if you can say something about hi of the top degree cohomology of z mod p to the n twisted by I, that it's all coming from units in sort of local units on the scheme. And so that says something about the image of this comparison map above. So this controls the image of the comparison map. In the top degree. Okay, so with this in mind, I want to make the following definition. So definition, and so this is due to Geisser, Sato, and Schneider. So I'm going to define the p-adic etale tate twist so what we're going to do is we're going to take this truncation tau less than or equal to I. So we're going to start with this truncated push forward of the usual tate twist. And we're going to sort of, so this lives in degree 0 through I. So what you can do is that you can replace the top degree cohomology by some subsheaf. And we're going to modify this in hi by basically doing sort of taking into account the above fact. So by taking the subsheaf generated by symbols from OX cross. Right, and so here what happens is that you're using the Kummer map. So here you're using the Kummer map, which goes from units on x adjoin 1 over p to, sorry, I guess let me say it this way. So it's going to go from j lower star of OX cross adjoin 1 over p to R1 j lower star of mu p. So you can always use units in x adjoin 1 over p to give you classes in hi of these so-called p-adic nearby cycles. And what you want to do here is you want to take the sort of the subsheaf that's just generated by local units that are actually living over x. Okay, but so basically you're just sort of modifying it in the top degree to to make this fact, to sort of take into account this fact that about the top degree cohomology of the z mod p to the n twisted by I. Okay, and so basically the phenomenon is so you get a comparison map. So sort of by the above, you get a comparison map which goes from z mod p to the n twisted by I sub x to the p-adic etale tate twist. Well, to the appropriate p-adic etale tate twist with weight I and mod p to the n. Yeah, and so basically the phenomenon is that this map often ends up being an equivalence, and there's various results in the literature to the effect that this is an equivalence in some cases. So, right, so let me just say that this comparison is often an equivalence. And okay, so I wrote this ahead of time. So basically, I think this has been considered quite a bit if you have a DVR. So if you have a complete DVR of mixed characteristic and you have a smooth scheme either over that DVR or over its absolute integral closure. And so then the theorem is that the comparison between the z mod p to the n twisted by I sub x and the p-adic etale t twist is an equivalence in these cases. Well, so first of all, so let me say this. So there's a result of Kato that if you have a smooth scheme over OC, then this comparison map is an equivalent sort of in low weights, in weights up to p-2. And then there's one sort of result of Kurihara that if instead you have something smooth over a DVR, again in the same range, this comparison map is an equivalence. And then there were results that these comparison maps are equivalences in all weights, but up to isogeny. So when I say up to isogeny, I mean that, well, you're saying that you have some map mod p to the n for each n, and that map is an equivalence up to denominators that don't depend on n. So if you have something which is smooth or semi-stable over OC, then this was proved by Tsuji that the comparison map is an equivalence, again, up to isogeny in all weights. And if you have something smooth or semi-stable over OK instead of OC, so K is, again, something that's discretely valued, then this was proved by Gomez and Niziol. Right. So yeah, so let me say a little bit about, these theorems were formulated in a somewhat in a slightly different fashion. So in fact, the theorem, I mean, all the action is really happening on the locus where p equals 0, because already we already know what happens when p is invertible. And these results were formulated in terms of syntomic cohomology. So they're not quite formulated in this way in terms of these z mod p to the n twisted by I, but they're formulated in terms of syntomic cohomology as defined by Fontaine-Messing. And the idea of syntomic cohomology as well. So I'm just going to scroll back up a little bit. So if you look at this description by Bott-Moreau-Schulze of the z mod p to the n twisted by I, when you restrict to p equals 0, it's in terms of prismatic cohomology. And these results were formulated before prismatic cohomology, but they're sort of a similar thing that you can do with Derived Derived cohomology or Prism cohomology in terms of instead of prismatic cohomology. And so then that's called syntomic cohomology. And so in the paper with Antio, Moreau, and Niklas, there's this comparison between syntomic cohomology and the BMS2 complexes. And that's sort of why things are, and so it's because these results are formulated in terms of syntomic cohomology is why they're formulated in weights up to p-2, or they're formulated with this up to isogeny. But there are also results that hold integrally and in all weights. And this is sort of more recent because it comes after the work of Bott-Moreau-Schulze. And so already in BMS2, and then also extended to a semi-stable case by Gomez, Desminescu, and Niziol, it was shown that if you have something which is smooth or semi-stable over OC, so here C is some complete algebraically closed non-Archimedean field, then the comparison map is an equivalence in all weights and integrally. So this is sort of more recent. Okay, so I guess so maybe I should say so one case that I think already has sort of not covered by these results is not covered is something like a smooth algebras over OK or ZP or something, or a discretely valued case. Okay, so what I wanted to do is to describe sort of a class in this talk. I wanted to describe a class of schemes for which this comparison map is an equivalence, and in particular, this will sort of imply these or sort of include these results that I've mentioned here. Okay. Okay, so the basic definition is the following. The basic definition of this talk is the following. So let R be a p quasisyntomic ring. And so we're going to say that R satisfies the Siegel conjecture if the following holds. So what I'm going to do is I'm going to consider the prismatic cohomology of R. And so there's some sort of structure associated with this. So if you have the prismatic cohomology of R, right, so it has a Nygaard filtration. And the first thing I'm going to do is I'm going to take the ith Nygaard piece of the prismatic cohomology of R. Right, and so this is the absolute prismatic cohomology of R. And this ith Nygaard piece of prismatic cohomology, it comes with the following operator. So it comes with a divided Frobenius called p-adic. And that lands, well, not quite in the prismatic cohomology of R, but in the Hodge-Tate cohomology of R. And here I'm going to Nygaard complete. So this is the ith Nygaard piece of prismatic cohomology. And this is the, sorry, there's a break kiss and twist by I. So this is the Nygaard completed Hodge-Tate cohomology. And this is the ith Nygaard piece of prismatic cohomology. Okay, so sorry, I didn't write a complete sentence yet. So we're going to say that R satisfies the Siegel conjecture. So if for each I greater than or equal to 0, this map phi-adic, which go as follows, has the property that the fiber, the homotopy fiber of phi-adic, which is going to live in the, I guess, the p-complete derived category of R, and the condition is that it should have p-complete Tor amplitude. In degrees greater than or equal to I plus 2. So it's some sort of homological condition on the prismatic cohomology, and we're in particular about this divided Frobenius from the Nygaard piece of prismatic cohomology to the to this Hodge-Tate Nygaard completed Hodge-Tate cohomology. Right. So maybe I should say something about the name. So in fact, this is this map. Right. So this map phi-adic, it arises from the cyclotomic Frobenius. So it arises as well, it's the ith associated graded up to some shift of the cyclotomic Frobenius. Which is a map that goes from THH of R, p-adically completed, to THH of R, Tate CP. And so the cyclotomic Frobenius plays sort of a central role in the approach to topological cyclic homology and cyclotomic spectra developed by Nikolaus and Scholze. And right, so in fact, this was this sort of came up in Thomas Nikolaus's lecture just before. So in fact, this sort of saying that this type of cyclotomic Frobenius is sort of an equivalence or an equivalence in high enough degrees is often called the Siegel conjecture for reasons coming from algebraic topology. And essentially, this condition is saying that you have something like that at the level of associated graded pieces of the filtration that was defined by BMS2. But in fact, it's actually sort of a purely, if you say it like this, it's sort of a purely algebraic condition, but it so it is closely related to algebraic topology as well, and the spectral Frobenius. Okay, so let me say a little bit of, let me give some examples of this condition. I think it would be interesting to try to understand this sort of class of, would like to sort of have more examples of this class of rates, but let me give some examples that I'm aware of. So the basic example I wanted to mention is that it's true for regular rings. So regular rings satisfy the Siegel conjecture. And right, so let me say a little bit about why. So first of all, for FP algebras, so regular or sort of in-smooth FP algebras satisfy the Siegel conjecture, and that is essentially the Cartier isomorphism. The fact that regular rings satisfy the Siegel conjecture is essentially the Cartier isomorphism, because prismatic cohomology is basically crystalline cohomology in this case, and sort of, yeah, you can identify all of this sort of very explicitly in terms of these constructions. And the idea is that you can actually reduce to the case of FP algebras via degeneration argument. So what you do is you use the following degeneration argument, and this argument is due to Hahn and Wilson in a somewhat different setting. So essentially, you can reduce to the case of a complete regular local ring, and then you give it the m-adic filtration. And the associated graded is going to satisfy the Siegel conjecture by the case of FP algebras, which we already saw. And then that means that R itself is going to have to satisfy it, sort of, yeah, by degeneration. Right. So in general, I guess I think the philosophy is that this definition is somehow it's some notion of regularity that, well, first of all, I guess it's only a p-adic notion. Everything only depends on the p-adic completion. So it's some sort of generalization of the notion of regularity that makes sense in sort of very non-Noetherian settings as well. Yeah, so let me just sort of give a couple of more examples. So another example is that this has been studied. So this condition, the Siegel conjecture, has been studied for FP algebras by Kelly and Morrow and Kurtz-Strunk-Tama. And it's called Cartier smoothness. So we call it Cartier smoothness. And let me just sort of explain explicitly what the condition is. So the first condition is that the cotangent complex of R over Fp should be a flat R module. And then second is that you have a Cartier isomorphism. So you have the Cartier isomorphism, which means that so you have the inverse Cartier map from I-forms of R over Fp mapping to the ith piece of the Theorem complex of R over Fp, just the classical Theorem complex. And that map should be an isomorphism. So yeah, so these two conditions are, they call it Cartier smoothness. And so, for example, one thing that's right, so one thing that's kind of nice about this, and so that they prove, is that, so remember there was this description of the Fp of i's for smooth or for regular Fp algebras. And in fact, it's true for any Cartier smooth Fp algebra or any Fp algebra satisfying the Siegel conjecture. So what they show in their work is that if you take Fp of I on spec R, it has the same description in this case. So it's given by omega I log shifted by minus I. Okay, so let me give a couple of more examples. Right, so another example is that this is true for, right, so, okay, so for example, perfect Fp algebra satisfy this, smooth algebras over perfect Fp algebra satisfy this. But you can also extend this to mixed characteristic. So perfectoid rings or smooth algebras over perfectoids. And so this is already treated in BMS 2. And more generally, right, so more generally, you can study this condition for algebras over a perfectoid. So this has been done in work in progress of Vincent Bouy. So the condition has been studied for algebras over a perfectoid by Vincent Bouy. Sorry. Right, so I think Bouy also proves at least most of the main sort of results I'll explain in a second. Yeah, so just one more example is that the Witt vectors of a perfect ring. So you can see this using the same sort of degeneration argument of Hahn and Wilson. I think also there should be a purely prismatic argument, both in this case and in the case of regular rings, but don't quite understand the details just yet. So, okay. Yeah, and I could also say smooth algebras over this. So it's sort of, yeah, so this condition is also sort of, it's sort of robust in some sense that it works for, you know, it's stable under passage to smooth algebras, and it's closed under filtered colimits and so forth. Okay, so let me state the sort of main theorem. So I guess this is proved with Bott, and I think also, as I said, some much of it has been proved by Bouy over perfectoids. So and the statement is the following. So let X satisfy the Siegel conjecture. So X is I guess, right. So it's always a p quasisyntomic scheme. And suppose X is p torsion free. Right, so then the statement is that the comparison map is an equivalent. So then the z mod p to the n twisted by I sub x is equivalent to the p-adic etale tate twist. So if you satisfy the Siegel conjecture, then the comparison map is equivalence. Yeah. So in particular, this applies to say regular rings with mixed characteristic. Okay. So right. So I still have. I guess I still have some time. So maybe I can say a little bit about the proof of this result. Right. So the proof of this result is essentially it's essentially sort of a bit of linear algebra with the results of with the techniques of BMS2, and one of the key ingredients is the etale comparison theorem. So the proof of this result, it's based on the etale comparison theorem. So due to Bada and Schulze and their prismatic cohomology paper. And actually, I want to sort of formulate the etale comparison in terms of these z mod p to the n of i's. Right. So let's formulate it as follows. So there's a class which I'm going to call v1, and it lives in H0 of fp with weights p minus 1 of the integers. So if you evaluate this weight p minus 1 complex from the integers, there's a class that I'll call v1, I guess maybe defined after scalars. And for example, you can construct this class using stable homotopy theory, but I guess it's not, well, you can also say it's sort of algebraically. So, right, so for p equals 2, this class v1 is the image of minus 1 under the Kummer map. Right, so minus 1 is a, well, sorry, so I guess so minus 1 is it's the square root of 1, so it gives you a class in H0 of fp f2 of 1 via the Kummer map. And for p odd, well, over z adjoint zeta p can do the same. So you take the class of a primitive p root of unity. But that's going to live in fp of 1, and then you sort of take the p minus first power of that, and that is going to be defined over z. So yeah, you can also construct it, I guess, for p odd using stable homotopy theory. So take p minus first power, and that's why you get a class in weight p minus 1 instead of in weight 1. And so then there's the following sort of right. And there's the following version of the etale comparison theorem in terms of this class v1. And so it states that if you invert this class v1, then what you're getting is so if you have any scheme x, well, let me assume x is p quasisyntomic for simplicity. Then if you take this direct sum of the fp of I of x, this is, I guess it's like a graded E infinity ring, and it has a class v1. And if you invert this class v1, what you get is exactly the same thing for x adjoin 1 over p. So it's given by direct sum, and now I should say all I an integer of fp of I of x adjoin 1 over p. And well, right, so I guess by definition, this just means the etale cohomology of x adjoin 1 over p with coefficients in mu p tensor I. So the statement is that if you have this element v1, or you could call it like a bot class, when you invert it, you get exactly the fp of i's of x adjoin 1 over p, which is just etale cohomology. So this is some form of the right. This is sort of a reformulation of the etale comparison theorem in terms of these complexes. And so then the idea is that, well, if you want to prove this theorem, so this theorem about this identifying the z mod p to the n of i's in terms of the p-adic etale tate twist, well, essentially what you're doing is that if x satisfies the Siegel conjecture, right? So you're comparing fp of I of x to fp of I of x adjoin 1 over p. And then, well, you have to say something in the top degree as well. So it's sort of enough to show that the map from fp of I of x, given by multiplication by v1, to fp of I plus p minus 1 of x is sort of an isomorphism in degrees less than I, in cohomological degrees less than I. Right, and so, well, again, so everything, all the action is really happening at sort of the p-adic locus. So sort of reduce to the p-adic locus, and you use the BMS2 formula for fp of I of x as an equalizer. And then what it essentially amounts to sort of, and then it's essentially sort of a linear algebra argument, which, well, maybe I should not try to give right now, but it's basically a linear algebra argument with this BMS2 formula. And an input to this, to make this linear algebra argument work, is actually Boeksted's description of THH of Z with p-adic coefficients, and in fact, the prismatic cohomology of Z, or the pod-shape cohomology of Z with p-adic coefficients. Yeah, so it's a fairly simple sort of linear algebra argument when you use this, and then you also need the Siegel conjecture to see that one of the maps is an equivalence in that case. So that's basically the idea. So since I still have a couple of minutes left, let me just sort of also say something about some related work, which, well, it's what I believe is related work, though I would sort of like to understand the relation better. So essentially what we're doing is, well, this is sort of closely related to computations of TC of regular rings in mixed characteristic. I mean, so what we're doing is we're not quite computing TC, but we're computing the associated graded pieces of the BMS2 Mathew filtration. But there's actually there's a rich literature of computing TC of regular rings in this context. So so there's work by Hasselholt and Madsen. Hasselholt and Madsen, and Geisser and Hasselholt. And I think this is, I think mostly in the case of smooth algebras over DVRs. And in their work, they compute TC somehow using the more classical approach to TC that before the work of Niklaus and Schulze, so using TR and using connections with the de Rham-Witt complex. And these calculations have also been revisited in very recently by Liu and Wang using the Niklaus and using the approach of Niklaus and Schulze. So yeah, so there should be a relation between some of these results and some of these calculations. Although yeah, so we're really computing associated graded pieces rather than TC itself. But somehow this was part of the motivation. Maybe I can also say that part of the motivation for all of this and of these types of truncations that come up in the p-adic etale tate twists is really the Berenson-Lichtenbaum conjecture on the generic fiber. So that's sort of the motivation for some of this work here. But okay, well, actually that's all I wanted to say. So I thank you very much. I'll stop here.
Well, thanks, Akhil. Other questions?
Hi, could you please explain how the Siegel conjecture condition follows from Cartier isomorphism in regular case?
Sure. Sorry, I should go back to the screen share. Sorry, regular and equal characteristic or mixed characteristic?
I think it was, yeah, over FP, but I mean, either would be good.
Right. So over FP, right, so the Siegel conjecture over FP, right, so I guess what happens is that in this case, so I guess this is in BMS2 and also in the Prisms paper, I mean, so this this Nygaard piece of prismatic cohomology of R, so if R is a, let's say it's a smooth FP algebra, then this Nygaard piece is exactly, right, so actually they identify it with tau less than or equal to I of the de Rham complex. So it's this truncation. And the Hodge-Tate cohomology.
Sorry, but shouldn't it? Okay, so right. Delta R will be just crystalline cohomology, right?
Right. So delta R is the crystalline cohomology. And the Hodge-Tate cohomology of R is exactly the de Rham cohomology. Well, I was going to say derived de Rham cohomology, but here we can just say de Rham cohomology. And I mean, right, so that's sort of this feature when you have, so I guess the general statement is that if you're over a prism, I think, then there's this, if you take the ith Nygaard piece going from
it's prismatic, a graded piece. Okay, I
yes,
see. Yeah.
It's a graded
I thought
piece.
It's now I understood, yes.
Yeah, right.
Okay. Then, yeah, I guess it's obvious. Okay. Thank you.
Yeah, thanks.
More questions? I had like one or two. You mentioned it's one of the cases where this has been proved before. It's a case where it's semi-stable over OC, I believe, right?
Right.
Does this satisfy the Siegel conjecture? Because it's not semi-regular in any sense, is it?
Yeah, sorry, I think so. There you have to take into it, it's with the log structure. So, so I think with the log structure, then I think it's okay. So I think so. One way you can think it, right? So one way you can approach these like log THH is through this infinite root stack procedure, taking the infinite root stack, and I think that will sort of be in the world of, say, so if you have something like the infinite root stack of something semi-stable over, I think that will give you something that's sort of irregular or satisfies the Siegel conjecture. I don't think it completely checked it for semi-stable over OC, but hopefully it's still okay.
But you still get the statement as stated, or do you get a log variant of the statement?
Oh, so then everything is the log variant. Yeah, sorry. I should have, yeah. So this comparison, so you can define all, right, so you can define these objects for log schemes, these z mod p to the n of i's, for example, using this infinite root stack. And then it's really the log statement that I had in mind. Yeah.
Okay.
Yeah. Thanks.
And a question I had is that for some of these results, I think over OC, you don't have to make this restriction that in top degree you're generated by symbols, right?
Yes.
Do you understand in which situations you would expect that you don't have to make this restriction? Or
so yeah, that's something I've been wondering about. Yeah, thanks for asking that. So yeah, so right, so there, I guess let me just scroll up to the definition. So right, so if you're over for smooth algebras over OC, so as in BMS2, you don't actually need to modify. I mean, in the definition of this p-adic etale 2H twist, it's sort of redundant. And my hope is that this should only happen. This is only a condition on H1. So my hope is that this is just a condition on units, so that sort of units p-adically in R join 1 over P come from R. And I guess my hope was that these p-adic nearby cycles, so these HI of Rj lower star of mu p to the n tensor I is sort of generated by symbols in degree 1. So this has been proved in many cases, like Blackato and Hyodo. And I guess I was hoping that it would be sort of true sort of generally, and then it would just be a setting in weight 1. But actually, yeah, I don't quite understand that. I'd like to understand it better.
Cool. Sorry, just to follow up, I have a very simple question. So, yeah, is it true that if you have two infinite root stacks which are isomorphic, then the log schemes are also isomorphic? Is that true in general?
So I think something like this is true. I think it's in this paper by Talpo and Vistoli. And I think if I remember right, it's not fully faithful, but you can sort of detect isomorphism classes, if I remember correctly, at least if you have the
Okay, right.
finiteness hypotheses.
So the functor from the log schemes to the stacks, to the infinite root stacks, that's not a fully faithful functor in general.
Yeah.
Right. Okay. Okay. Thanks. Thank you.
Yeah.
Further questions? That doesn't seem to be the case. So let's thank Akhil again.
Yeah, thanks everyone.
And yeah, thanks again to all the speakers and to the organizers for this really wonderful conference. It's been a really great pleasure watching this.
Great, so I think
the Fields Institute for hosting.
I think the Fields Institute wants to say something.
Okay.
Hi everybody, I'm Kumar Mathew. I think we've met perhaps before at the beginning of the conference. I just am charmed by the way the conference has gone. It's gone really well. I think thanks to the organizers, Anna, Bhargav, Ila, and Matt, and of course Peter. I remember when we started talking about this a couple of months ago. You had very clear ideas about what you wanted to do, and you brought it together really quickly. I was able to attend a few of the talks. It's clear they're very high quality, intense, but fortunately we've got everything's archived, so I hope to catch some of the reruns and see the talks that I've missed. I do hope that some of the graduate students survived, and that the things they heard, even if they couldn't understand everything they were hearing, that at least it would influence their research directions, and that they derive some long-term benefit from it. In the current circumstances where we have to meet online, this is sort of the best we could do, and I think in these contexts it came off fairly well. So thanks to all of you for your cooperation and participation in that, and I hope it was an enjoyable experience for all of you in this way. I eagerly look forward to, as I'm sure you do, to when we can all meet in person again, and that has its own energy, of course. But we're not letting this stop us from doing what we like to do, namely discuss mathematics. So we're doing this through this online format. I might mention that in the context of meeting in person, the Fields Institute has a sort of a mantra, that says that we want to make it as easy as possible for people to organize things and get together. That's why we're here. And so what I want to suggest to all of you is that take the opportunity. If you have an idea for a workshop, for a seminar, or for a longer term program, it's not onerous at all to make a proposal. And I would really actually be interested in having proposals that look to the study of perfectoids and their applications in all its manifest forms. So keep that in mind. The Institute exists to help people get together and collaborate. So do please take advantage of that. In addition to the scientific symposium, our public opening, I think, also went off very well, thanks to, again, the cooperation of everybody. We've got a lot of positive feedback, more than 3,000 views now, and it keeps going up. So all told, I think it was a successful event. Again, I hope that all of this has benefits to you, all of you, in terms of your own research and teaching, and somehow we will be able to meet again in the near future. So good luck, everybody. Thanks for joining, participating, and I hope to see some of you or all of you again sometime in the near future.